In this video, I'll be explaining linear programming problem using graphical method. We have here a maximization problem with the objective function to be z equal to 5x1 plus 4x2, subject to x1 plus x2 less than or equal to 6, 2x1 plus x2 less than or equal to 8, x1 plus 2x2 less than or equal to 10, where x1 and x2 is greater than or equal to 0. So first of all, to solve this problem, this is our constraint. We have three constraints here. We have constraint 1. This is the second constraint. This is the third constraint. So we are going to convert this inequality to an equality sign before we solve this problem. Converting this to an equality sign, we consider for constraint 1, which says x1 plus x2 equal to 6 for constraint 1. In this equation, we are going to find the value of x2 when x1 is 0, and we are going to find the value of x1 when x2 is 0. So when x1 is 0, what will be the value for x2? Therefore, we're going to substitute these into this equation. We are going to consider that for constraint 2 and 3. But first of all, let's focus on constraint 1. So when x1 is 0, we have, remember x1 here, 0 plus x2, which will give us 6. Therefore, our x2 will be equal to 6. The same thing when x2 is 0, what will be the value for our x1? Therefore, we substitute this into this equation. We have x1 plus, remember x2 is 0, equal to 6. Therefore, we have here x1 to be equal to 6. We can represent this on a table. Here is our x1, x2. So when x1 is 0, the value for x2 is 6. And when x2 is 0, the value for x1 is 6. We'll also do that for constraint 2. For the second constraint, we have 2x1 plus x2. Remember to change it to an equality sign equals to a's. Therefore, we consider when x1 is 0, what will be the value for x2? And when x2 is 0, what will be the value for x1? So for x1 to be 0, what will be the value for our x2? Therefore, we're going to substitute this into this equation. We have 2 times 0 plus x2 equals to 8, which will give us x2 to be equal to 8. We also consider when x2 is 0, what will be the value for our x1? So we are going to substitute these into this equation. We have 2x1 plus when x2 is 0, we have 0 equals to 8. Therefore, we have 2x1 to be equal to 8. Therefore, our x1 will be 8 all over 2, which will give us 4. So here, our normal diagram. When x1 is 0, the value for x2 is 8. And when x2 is 0, the value for x1 is 4. So for the third constraint, we have x1 plus 2x2 equal to 10. We need to find the value for x2 when x1 is 0. We need to find the value for x1 when x2 is 0. So when x1 is 0, what will be the value for our x2? So we're going to substitute this into this equation. We have 0 plus 2x2 to be equal to 10. Therefore, our x2 will be 10 all over 2, which will give us 5. Therefore, our x5 is 2. We also consider that when x2 is 0, what will be the value for our x1? We are going to substitute these into the equation, which will give us x1 plus, remember, x2 is 0 plus 0 equals to 10. Therefore, x1 is equal to 10. And we represent that here. We have when x1 is 0, the value for our x2 is 5. And when x2 is 0, the value for our x1 is 10. So the next thing we are going to do is to represent this first constraint, second constraint, and the third constraint on our graph to know our feasible region. To represent this on a graph, we are going to consider our constraints. Remember, for our constraint 1, which we solved together, when x1 is 0, x2 is 6. And when x2 is 0, our x1 is 6. The same thing with our constraint 2. Our constraint 2, which says when x1 is 0, x2 is 8. When x2 is 0, x1 is 4. Same with the third constraint, which says when x1 is 0, x2 is 5. When x2 is 0, x1 is 10. So we will represent these on a graph. So first of all, for constraint 1, which says when x1 is 0, x2 is 6. When x2 is 0, x1 is 6. So from our graph here, this is our x2, the y-axis, and the x-axis is our s1. So when x1 is 0, the value for x2 is 6. So the graph when x1 is 0, the value for s2 is 6. And also when x2 is 0, the value for our x1 is 6. We have 6 here. So we are going to join the two lines together. This is for our first constraint, which is constraint 1. So for our second constraint, when x1 is 0, x2 is 8. When x2 is 0, x1 is 4. We'll be representing that in our graph. When x1 is 0, the value for s2 is 8. When x2 is 0, the value for our x1 is 4. We have when x2 is 0, x1 is 4. We are going to join the lines together. Same thing for the third constraint. When x1 is 0, x2 is 5. And when x2 is 0, our x1 is 10. We represent that on a graph. When x1 is 0, the value for our x2 is 5. And when x2 is 0, the value for our x1 is 10. When x2 is 0, the value for our x1 is 10. So we have here 10, 0. x1 is 10, x2 is 0. So we are going to join these two lines together. Remember, this line is our first constraint. This one here is our second constraint. And the last one, which we did now, is our third constraint. So to consider our feasible region, from the constraints, the inequality sign is less than. When we have less than, our feasible region, the line will be below the line. So here is less than. So our feasible region will be below the line. Same thing with this. This is less than. The feasible region will be below the line. Same with the third constraint, which is less than. It's going to be below the line. But take note that if it's greater than, your feasible region will be above the line. So I'll show you what I'm saying here. So for constraint 1, the feasible region is going to be below the line, everything below. So our feasible region is everything here. This is above the line. For constraint 2, which is this, is also less than. So everything below this line, below the line, is our feasible region. So we are going to clean this. So everything below here is our feasible region. For our third constraint, which is this, everything below this line is our feasible region. So everything below the line, which is this, is our feasible region. So from here, we have our feasible region is just these corner points here, here, and here. So we have A here, we have A, we have B, we have C, and we have D. So from here, 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 and here is our feasible region. So now we are going to, from our feasible region, we are going to get the corner points, the value for each point. For point A, we have here 0. So we have here 0, 0. For point B, we have 4 and 0. That's x1 is 4 and x2 is 0, is on the baseline, 0. For C here, so we're going to trace this line to get the value. When we trace this line, we have 2. x1 is 2. And for x2, we trace the line, which will give us 4. So for C point, we have 2 and 4. For D, which is here, is 0 and 5. So from here, we have A corner point is 0, 0. Our B corner point, which is this, 4, 0. Our C corner point, which is here, 2, 4. And our D corner point, which is here, which is 0, 5. So we are going to substitute these in our objective function to know the optimal solution. Remember, this is a maximization problem. So from our objective function, we are going to substitute the corner points which we got. For A here, remember for A we have 0, 0. For B we have 4, 0. For C we have 2, 4. For D we have 0, 5. So for A, which is 0, 0, so we have for A, which is 0, 0. So when we substitute these into this equation, we have 5 into 0 plus 4, 0. We have 0. For corner point B, we have 4 and 0. Therefore, we say 5 times 4 plus 4 times 0. 5 times 4 is 20. 4 times 0 is 0. 20 plus 0, we have 20. For corner point C, we have 2 and 4. 2 and 4. So we have 5 times 4. 5 times 2, sorry, plus 4 times 4. So 5 times 2 is 10, plus 4 times 4, 16. 10 plus 16, we have 26. So for D corner points, we have 0 and 5. Therefore, we say 5, which is this, times 0 plus 4 times 5. So 5 times 0 will give us 0 plus 4 times 5, which is 20. 20 plus 0, we have 20. So from the values we have, which is 0, 20, 26, 20, can you tell me the highest number here? The highest number here is 26. So here the optimal solution for Z is 26. At which corner point? Guess, at 2 and 4 from our graph. At x1 to be 2 and x2 to be 4. So this is our solution. So if this video interests you, hit the subscribe button, like the video, and also comment. Thank you.